type of microscopy we are dealing. So very common optical microscopy I will cover. Then I will try electron microscopy, maybe SEM, FESM, TEM, or HRTM, whatever the case, is almost the similar type of electron microscopy and optical microscopy. And then if I will get the time, maybe I think I will go brief about scanning probe microscopy, which is scanning tunneling microscopy or atomic force microscopy or magnetic force, whatever the case, the forces we have. So we can have SPM. So I will try to explain all fundamentals of the microscopy. Okay. So a very common concept, microscopy. Why the word microscopy is derived, and you know that ever since the dawn of science, there has been an interest in being able to look at smaller and smaller details. So like biologists have wanted to examine the structure of cells, bacteria, viruses, and colloidal particles. Material scientists have wanted to see inhomogeneities and imperfections in metals, crystals, ceramics. So in diverse branches of geology, detailed study of rocks, minerals, and fossils could give valuable insight into the origins of our planet and its valuable mineral resources. And now more interest comes into functional materials, nanomaterials, or we call it advanced materials. Okay. So the challenge to the materials community is to make a difference by helping in the development of innovative solutions to important societal problems and supporting economic growth and competitiveness. So all this is possible by advanced materials. Okay. So they are associated process technologies with potential to be exploited in high value products and considered within major 4 areas: structural materials, functional materials, multifunctional materials, biomaterials, and of course now a lot of nanomaterials or nanotechnology. So effectively we say the functional materials are ubiquitous new materials with improved functionality exhibiting more than 1 degree of functionality will appear to provide even more applications. So what we require basically for the functional materials to design and synthesize, to understand the morphology or manipulate the morphology, interfere and transport electrodes, novel device architecture, or further lot of other applications. So today we know so many technology is already there in our day-to-day life, like light emitting diode, DVD player, liquid crystal display, magnetic materials in recording devices, and so many other possible metal oxide nanomaterials for a lot of other applications. Okay, so whenever we deal with the materials, definitely we need to characterize the materials because we have to understand the materials. So for understanding the materials, generally we do the optical, and during old days the optical microscopy was very popular to understand the grain boundaries and other structures. But now the electron microscopy is more common. Everyone is going to smaller and smaller size of the particles. That's why electron microscopy, and then furthermore XRD and other technical characterization tools we need. So because my talk is only for the microscopic studies, so I am just focusing on microscopy. So just like I would like to say that optical microscopy is a very old phenomena. During 1800, so it started, and up to now the optical microscopy with advanced tools and advanced systems we have, like one of the picture at the end, this one we have at NIT Kurushetra. So this is again a materials microscope. Then scanning probe microscopy is also very popular because for handling the specimen or sample is easy in case of scanning probe microscopy. And then we have the electron microscopy. So just if you think scanning microscopy means from 1600 we have the light microscope, then 1938 we have transmission electron microscope, in 1964 we have scanning electron microscope, 1982 this scanning tunneling microscope is also an electronic microscope but based on SPM or scanning near field optical microscope, some further improvement in the optical microscopy, and then atomic force microscopy, under which magnetic force, lateral force, or other chemical forces we can utilize the fundamental physics, and then we can go for the scanning microscopy. Now, if you think why we are interested, basically, so if we use the optical microscopy, we can go beyond 1 micron or so, but below 1 micron, it is not possible. But if we say for mesoporous materials, so definitely it should be 2 nanometer to 50 nanometer range. So we cannot do any optical microscopy. So definitely we need scanning or electron microscopy or SPM, scanning probe microscopy. Or if we go further below, the microporous materials means below 2 nanometer pore size. So definitely we have to go for TEM or HRTEM or SPM. But HRTEM is or TEM is more easy as compared to SPM, because the setting of SPM is difficult at lower level. But as a fundamental physics, SPM is also possible with this. Okay, so why microscopy? Means how the materials are, let's say, changing the properties if you change the structure. Okay, so materials or nano materials or microstructures are more important for all type of materials. Either it may be the functional material, it may be the nanomaterials, because if you go to the structural size change, maybe the quantum confinement effect will occur, and in what region it could occur, what abrupt change in the properties it will play. So you have to understand the structural change in the materials. Okay, like thin film is a layer of material ranging from fractions of nanomaterials, like monolayer, to several micrometers in thickness. And the control thickness of materials as thin film is a fundamental step in many more applications. Now, the chemical composition is another important aspect to understand the material, allowing the materials. Speed of solidification means how you do the solidification of the material. So every time with the different temperature, with the pressure, and with the other environmental conditions, everything will change in this crystalline structure. Or heat treatment, if you do the materials, definitely there is a change. Or quenching effects, mechanical treatment. There are so many effects. All those effects could change the structural structures of the material. So definitely you need to understand the through the microscopy. Or if you say the typical impact of processing parameter on materials, it means percentage of phases, grain size, orientation, elongation, particle size is most important, shapes is further important. Another important nowadays, a lot of functional material properties changing on the basis of porosity, because we need light material. So if we create more and more porosity, we can create more surface area of the materials. Okay, so that is also important. Then the shape and size, microstructure anisotropy, or spacing between precipitates. Okay, so all these you can realize only with the microscopy. Means we want to see the materials. So thin films plays an important role in the development and study of materials with new and unique properties like multiferroic superlattice that allows the study of quantum phenomena. That all do, because if you have the quantum confinement effect, I hope you understand. Means let's say if the materials is, the size of the material is of the order of any physical quantity, it could behave as a quantum jump in the properties of the materials. It means quantum phenomena could occur. So we have to understand whether it is due to quantum confinement of the materials, in the materials the property is changing. So we just want all possible the materials properties, maybe some fundamental properties also. So act of applying any let's say the concept in materials, in the films, you always need the microscopy. Okay, so I can skip this. I'll just that's understanding of microstructure means understanding the materials. So overall, we have to understand the materials, and for understanding the materials, definitely we need to understand the structure, and to understand the structure we have to go to the microscopy. Okay, so all these global parameters of the materials we can understand by using the materials properties. Okay, so all these like fracture, crack propagation, fatigue properties, local corrosion, all these are also possible only by understanding the let's say the scanning of the materials. Okay, so the materials can be scanned very easily with the electron, optical, or scanning probe microscopy. So all these three microscopies are always required to understand the materials. So just for your reference, I will try to explain you the basic principles of the microscopy. And this microscopy means whenever you get the microscope, it means you are playing with the image analysis. So you are getting an image like let's say SEM or TEM, or you are getting, let's say, two-dimensional images. But if you want to get the three-dimensional image, generally SPM could play a better role, and you can get the three-dimensional image of the materials. Okay, so it means image has to be analyzed. Okay, so normally this microscopic image is done when you take the camera picture. So generally you have the CCD camera, charge coupled device. So that image captured and digitized it, because it gets the analog picture and then converted to the digitized image, and simply on the screen you are getting the digital image. So definitely you need the digitization image, and then you have to analyze it. So there are a lot of software through which you are analyzing the pictures. Okay, so just image J, one example in all same time we are using, or some QWin plus software is also there. It's just an example, solving power of microscope. So we just to understand up to what range we can go, up to what range the eyes can see, up to what range the microscope or electron microscope can go. So is again the similar type of concept, means up to micron level light microscopy, but up to angstrom level we can have the AFM, and this SEM we can go up to 1 nanometer to centimeter range, but with the TEM or HR TEM we can go up to angstrom or below that atomic level. You can see this image. So finally I start with what I would like, means the microscopy and why we need, as I explain you, because all the materials, if we want to understand, we have to understand the microscopy. And to understand the microscopy or image analysis, whatever the case, you have to understand the fundamentals of physics. So physics means, in case of optical microscope, if you see, so you understand the resolution and magnification. Okay, so I hope you understand that with our naked eye, we can reach up to 0.2 mm apart objects is the limit. Okay, but to the lower side, we have to let's say magnify the image, but only the magnification of the image is not sufficient. If the resolution is not proper, means more than 0.2 millimeter, we cannot observe. So definitely in case of any type of microscopy, magnification and resolution both are important. Okay, so in this case, if you say the fundamental magnification and resolution is generally of the order of 0.1 mm, it means we have to understand between, or let's say the compromise between magnification and resolution. If you want better resolution and better magnification, definitely we have to understand somewhere that what should be the better possible way, so that resolution should be better. It's not only you go for the higher magnification and you get the better result. No, you need the resolution also. Okay. And again, this is just because all the PPT is prepared for our MTech students, so just more contents are there. But just to understand here, the resolving power means the smallest resolvable separation between the two objects, means D minimum, and that is the given formula 0.61 lambda by numerical aperture. So generally this numerical aperture n is n sin theta depending on the refractive index. Also in case of optical microscope, because the lambda is magnification, means resolution you want better, it means lambda should be less. So in that case, the medium you are changing. So that's why in advanced materials, the lenses are dipped in the medium of higher refractive index, and then you change and you play with that, and you can go up to let's say the magnification up to 2000x with this with the materials microscopy, what let's say I have in my lab, up to 2000x, and resolution up to 0.5 micron or so. Okay, and again, if you convert this image to the digital image on the screen, generally there's another Nyquist criteria, which again say the resolution and magnification must be equal to 2 into the pixel size. Okay, so we have to understand what we want, what we have to understand. Okay, it's just the properties with the simple lens. If you say magnification Q by P, and then this Rayleigh criteria. So just we can skip this. Now, in case of light, what is the limit? Because the blue light is the lowest visible range we have, so that is 0.47 micrometer. So resolution means half of the lambda generally we can achieve, so that is 0.2 micrometer, means 200 micrometer, 200 nanometer is possible with the optical microscope. We cannot go beyond this even with all better possible optics. Okay, so generally resolution with the optical microscope is of the order of 0.4 micrometer. But if we want further improvement in the resolution, we need the smaller or the shorter wavelength. Okay, on the basis of de Broglie wavelength, we have to understand, then we think of. So just to show what we have at NIT Kurushetra, maybe you can think of to do the sample scanning here. So what we have, example of this optical microscope, this is Leica DM digital microscope, and this is having the important features, means contrast management, illumination management, functional keys, and lot of display here. So maybe I can explain further, because here this is the eye lens, and here we have the objective lenses. So different magnification objective lenses are there, and in between eye lens and objective lens there are the prism inside. So the prism is also magnify the image 2 times. So generally we have the maximum magnification with the objective lens is 100, then 2 times with the prism we can magnify to 200 times, and then multiply with the 10 of the objective X, eye lens of the 10. So effectively you can see 2000x magnification of the sample with that. And here we have the panel where we can control the brightness, we can control the position automatically also. Okay, so like focus position, the lower threshold, step size, objective speed. Another important concept with this microscope is we have the smart move. This here, the smart move means with the continuous movement of XY direction and Z direction you can do. So the accuracy of the movement is around 1 micron. Okay, on X and Y direction. So the controlling of the picture is also very accurate up to the micron level in this case of microscope. These are just some the concept of the image of this and how you acquire the image. So here we can say the magnification on the panel we can go. Okay, then you have how to acquire, how to see the image. Just an example here. We also having the fluorescent light. So if you have the material fluorescent material, so if you illuminate with the different light, you can also have the fluorescent images of the materials sometimes we need. Now, contrasting methods of microscopy means how you get, because every time you don't have the similar type of materials. Sometimes it is transparent materials, sometimes it is opaque type of materials. Okay, so how you illuminate, how you get the better image. So definitely the different possibilities is there. means bright field image, dark field image, polarized contrast image, phase contrast image, or interference contrast images are there. All these possibilities are there with the single system. So what does it mean basically? So bright field means the direct light reaches the objective, and diffraction, reflection, and absorption of light forms the microscopic image. And this brightness or resolution, contrast, and depth of the field are quick quality parameters of the image. So you have to understand what type of sample we have, and for what situation we need. Like dark field, again, direct light doesn't reach the objective, only the diffracted light forms the image. Okay, and well suited for all kinds of line structures. So if you see here, I can go a little bit here. The components of dark field, this one. You see here the normal picture, and if you see the dark field, so here the better clarity is there, the right side. Okay, so it depends how you want to, let's say, see your image. So dark field give you the better image sometimes. Sometimes the polarized light, polarized contrast is giving better image. So I think you can go. So just the polarized light and phase contrast, a sensitive method to convert phase differences into visible brightness differences. Okay, so a method for transmitted light microscopy, and for inverted and upright microscope, generally we have these type of contrast, illumination with angular diaphragm generally. Okay, so this is one type of idea. Then phase contrast, another method we have. So I think we can go for different type of sample, different of idea. And the similarly interference contrast we have for inverted and upright microscope. We have transmitted light and reflected light both. And then interference contrast means the part, the different prism, how to use this and get the better image. Now, the idea of image analysis, as I told earlier, also this Leica QN Plus is the software with the microscope software. So this is like in all type of scanning probe microscopy or in electron microscopy, everywhere you have the software, because all these electronic instruments cannot control with the man handedly. This is all controlled with the software. So that's why every system is having its own software. So just QN Plus is the software with the optical microscopy system we have. So this QN Plus contains all the commonly used facilities like field and feature measurements. It provides access to all menus and dialogues and works on pre-written QUPS macros. Means once you decide a type of programming and you give to the microscope, and accordingly it will work with your programming. So you can program whatever you want, what type of measurement you want. So everything you can play with this. So you have to write this QUPS macros in C or C++ generally, or Visual Basic also. So there are a number of parameters which can be measured in Leica software, like length, area, magnification, XY position, roughness, centroid, perimeter, number of counts, and also the histograms can be plotted to see the distribution. So sometimes for the particles or for the grain boundaries, histogram type of things we can have. Or in case of light microscopy, basically image analysis system is all through the camera, is like CCD, and interactive measurements for low number of features can be done, or automatic image analysis can be done with the or for higher statistical values, or all these possible in all digital work, we can say. So means digital image analysis. Okay, so digital, again, I would like to explain you what does it mean by digital, in what way, because when we see with the optical microscope, you are seeing the analog image. Okay, that analog converting to the digital, and how it is converting. So that is based on pixel to pixel concept. So we have to understand the resolution in terms of pixel, as I told you, Nyquist formula. Okay, so digital word is with the computer you are doing. So for example, if you go like this type of image, and what I want, if you magnify it, you have the simple image, but you further magnify, you see this part broken. Okay, so image is like some sort of blur, but you have to understand how the pixel to pixel analysis is possible. Like here, further if you enhance, the pixels are again broken. So it means the resolution of the pixel is not good right now. If if you deal with the all cameras, now basically the quality of the cameras improved a lot. Okay, so if more pixels means the size of the pixel is very small, so generally the pixel size in the case of TV screen or camera screen of the mobile, let's say, we have of the order of 0.4 into 0.4 micrometer square pixel size because of the limit of the resolution of the optics, means the wavelength. Okay, so it means you can play with this image profile. You can colorize the image. You can, let's say, even the pictures are attached, so you can break, you can cut these images, and you can understand all possible way. So just an example I would like to say here, because this is just an example of energy physics. What we are doing here means different size of the tracks are there. So what we can do, we can measure, let's say, enlarging the size of the defects in the thin film, and then you can measure the diameter very easily up to the accuracy of plus minus 1 micrometer. Okay, so that's the idea here. You can do this, so very accurately measurement of different pixels and different ideas. This is all automatic peripheral measurement of the tracks. Okay, so it means up to plus minus 1 micron is very good resolution, but here they are giving 0.4 and 0.1, but this is all the example, but with some error is there. So that's why you say approximately plus minus 1 micron is there. Like here, one pixel size is 1.16 micrometer. Okay, so if pixel size is of the order of 1 micrometer, it is beyond that, it is very difficult to understand below this micron size with this optical system. So that's why we generally say if we want the image up to the micron level accuracy, we should do the optical microscopy, not the electron microscopy. Okay. Just a brief about advanced optical microscopy, like confocal microscopy nowadays. So we don't have it, and even I am not expert in this this confocal microscopy because we don't let's say study it right now. But theoretically, what we know basically is all with this system confocal microscope we can go up to the nano level, with HD confocal microscopy. Okay, and using different type of modes like vertical scanning interferometry, phase shift interferometry, or extended phase shift interferometry for resolution up to 0.1 nanometer. But this is all let's say limited way to control the position, the movement of the things, and then there are some other advanced technologies. So just this Leica purpose, they develop this type of microscope, which is related to the confocal microscopy, but it is very expensive, so we don't have it right now. So this is all just with the optical microscopy what we have at NIT Kurushetra. Now, again, we go to electron microscopy, because with the optical microscopy, the limit is up to the micron level. 1 micron is you can assume very well resolution, and up to 1 micron we can think of all type of materials, either film or let's say thick type of materials. It depends on the size between stage and this objective lens, how much space is there. So up to that size you can keep directly and see it very easily. Okay. Now, because in case of functional materials, people are definitely going to the lower size of the materials, lower size of the pore size, lower size of the crystallite size. So definitely you need the electron microscopy, because we cannot understand anything below the micron by the optical microscopy. So this electron microscopy is just starting. And as you told, the resolution is limited with the wavelength of light. So definitely that technique that allows the examination of the samples too small to be seen with the light microscope, we have to understand the electron microscopy. Okay, so just in 1920s, it was discovered that the accelerated electrons behave in vacuum just like light. They travel in straight lines and have a wavelength which is about 100,000 times smaller than that of light. It was again found that the electric and magnetic fields have the same effect on electrons as glass lenses and mirrors have on the visible light, like electromagnetic lenses, we call it. In case of light, we simply say the glass lens. With this electron controlling, we have the electromagnetic lenses. Okay, so this Dr. E. Ruska at the University of Berlin combined these characteristics and built the first transmission electron. You see, the initial discovery was the first transmission electron microscopy, not the scaling electron microscopy. Okay, in 1931. For this and the subsequent work on the subject, he was awarded the Nobel Prize for Physics in 1986. The first electron microscope used two magnetic lenses. You understand? The magnetic or electromagnetic lenses, basically. And 3 years later, he added the third lens and demonstrated resolution up to 100 nanometer. Twice as good as that of light microscope, because the limit up to the 200 nanometer, but you can say the 400 nanometer, but 100 nanometer was achieved by this. But today we have better magnetic lenses and imaging system, and resolving power up to 0.1 nanometer can be achieved with this latest technology of TEM or SEM. Now, in this case, simply what we understand, maybe a lot of things is written here. I would like to say how you are changing the light source to the electron source with the use of electron gun, because this light source replaced by the electron gun, but these electron gun could be possible behave as a light in the vacuum. So that's why for its SEM or TM we need the vacuum. Okay, so these glass lenses are replaced by the electromagnetic lenses, and the eyepiece or ocular is replaced by fluorescent screen. Means the electrons either reflected, transmitted, or secondary, whatever the type of electrons. How you realize that? So this realization comes with the hitting of the electrons to some screen, which is, we call it fluorescent screen, and the entire electron path from gun to screen has to be vacuum. Otherwise, electron would collide with the air molecules and be absorbed. So the final image has to be viewed through a window in the projection chamber. Okay. Another important difference is that unlike glass lenses, electromagnetic lenses are variable. By varying the current through the lens coil, focal length could be changed, magnification could change. Okay, you can vary. In case of light microscope, variation in the magnification obtained by changing the lens or by mechanical moving the lens. But in this case, you just change the current, you can change the focusing and anything else. Okay, so just detail here may be given, but I think you can go further. It's not completely clear who first proposed the principle of scanning the surface of a specimen with a finely focused electron beam to produce an image of the surface. The first published description was in 1935 in a paper by German physicist Dr. M. Noll, although another German physicist who performed some experiment could be called a scanning electron microscope in 1937. And it was not until in 1942 that 3 other American scientists discovered with the magnification and resolution up to 50 nanometer and to 8,000x. Nowadays, the SEM is having resolving power up to 1 nanometer and magnification around 400,000x, means around 4 lakh. A combination of the principles used in both TEM and SEM, usually referred to as scanning transmission electron microscopy. We call it STEM, and was first discovered in 1938 by the Manfred von Ardenne, and it is not known what the resolving power of this instrument was, but the first commercial instrument in which the technique were combined with the Philips, and here this STEM developed by the Philips Company Instruments USA 1969. At the time of this, the resolving power was 25 nanometer and magnification was around 1 lakh. But now the magnification with the TM is around 4 lakh and 1 nanometer resolution or 0.1 nanometer resolution with the advanced HR10 we have. So in case of scanning electron microscopy, the magnification is entirely determined by the electronic circuit that scans the beam over the specimen and how this simultaneously over the fluorescent screen of the monitor where the image appears. So as I told you, is on the basis of electron beam hitting to the sample, what is happening after all these electrons and how these electrons are managed to get the image. Okay, so in that case, magnification up to 3 lakh is possible, and the resolution generally in the case of scanning microscope is up to the order of 1 nanometer can easily achieved, and the scan area generally of the order of few micrometer we can get. Just an old picture. This idea of the filament we have. So generally this tungsten source or LaB6 electrons people are using as a simple rod, and how you are getting the electron beam and how you are controlling with the cylinders. Sorry. Okay, so in that electron gun, basically it consists of a filament, wire-net cylinder, and is the same as that in the TM. So gun basically could be either TM or the SAM is the same. Okay, then the consisting of this electron gun means anode and condenser lenses is not much different. The final lenses focus the beam onto the surface of the specimen that has to be studied. So then, sorry. It means in that way how you are getting the beam current with the what type of gun source you have. Okay, so sometimes the pin type, sometimes this very sharp tip type gun the material you have, and you are getting the electrons, and then you are controlling with the cylindrical let's say shape of that gun, and you control with the lenses or anodes, you can say. In case of this tungsten or LaB6, there are the concept is like grid gap you are controlling with that, so that more electrons will be focused with other forces, and then you can have this type of cone of spreading of beam. So the cone angle is more important. So how much possible less cone angle if we could get better image spots. I will try to explain you how the image is the electron spot is important for the image analysis or for the resolution. But in case of field emission electron source, generally you have tip very sharp as compared to SEM, FESEM, very sharp tip, and through high field you are let's say emitting the electron. So that's why we call it field emission electron source. And with this again, the controlling the anode, you can control the beam spot very easily. Okay, so just in case of SEM and field FESEM is the only the difference in the source. What type of source you are using is electron source or electron gun you are using. Okay, so in that case, simply SEM, you have the electron gun here, and then you are controlling with the lenses, means all the electromagnetic lenses simply you have, or at the end you have simply the scan coil. So it's also a type of coil where we can change the current and we can control the spot which is falling to the sample. Okay, and then falling with the sample and what type of emission of the electron is happening, these electrons are detected with different type of detectors based on what type of energy range you are let's say interested in, and what type of image you want. Okay, what type of your sample you have. So you have that all connected with the computer, and then you simply control. Okay, here you can control the wavelength on the basis of, let's say, applied potential, while the say the velocity. Okay, so definitely you can change the let's say the wavelength you can change. So effect of increasing voltage in the electron gun means resolution is increasing, means you are decreasing the wavelength, because wavelength velocity is increasing, wavelength is decreasing. Okay, penetration increases, specimen charges also increases. So in that case, in case of insulators, you have to think of, so that you can avoid the charging effects on the surface. So it means to increase further, you could damage the sample. Okay, so you have to compromise between your sample to the resolution limit to the magnification, and you have to decide which is better possible way. So that's why you need a lot of expertise in the case of SEM or TEM. It's just the facility what we have at NIT Kurushetra, the SEM, the system. And here this is the coating unit, because when you deal with the non-conducting type of samples, and you have the charging effect, so to avoid that, you always need to coat the surface of the specimen, so that the charging effect could be avoided. Okay, so this is the coating unit, and you have the system. Here we have the detector for EDS also. This is Rutherford detector company, and this is just the phenomenon. This is just a schematic diagram what we have on the net. Simply just I took different type of lenses, different type of locks, how to control, how to, because you need the vacuum here, so how you automatically control the vacuum. Otherwise, every time you do the vacuum, and when you take the sample away, all vacuum will be finished. So you have to manage that, so that the vacuum should be remain there, and you could change the samples. So these are some idea about motorized system and how you do it. Okay, so in case of TM, it can be compared with the slide projector, like this. In case of SEM, I would like to explain you the later in the later stage. But in TM, what we are doing, transmitted, means the electrons are transmitted to the sample. So it means the sample should be very thin. So it can be compared like with a slide projector. When you say the old time, I hope, I don't know how many would have you seen the projector, slide projector, when we were keeping the projector on the slide, and that the written material coming on the projector. So it means light transmitted and getting the projector. So, but now we have advanced projector, not this simple slides, but it is the all techniques. But you can compare how it is happening in case of TM. Light from a light source is made into a parallel beam by the condenser lens. This passes through the slides and is then focused as an enlarged image onto the screen by objective lens. In electron microscope, the light source is replaced by the electron source. The glass lenses are replaced by the electromagnetic lenses, and the projection screen is replaced by a fluorescent screen which emits light when struck by electrons. So whole trajectory from the source to screen is under vacuum, and the specimen has to be very thin to allow the electrons to penetrate it. Like earlier we have the transparency, means it should be transparent to the light. In the same way, but we have the sample, it should be thin enough so that the electrons should penetrate, because what the energy limitation we have, so it should penetrate. Okay, so generally for the TM we have to prepare the samples. I will explain it later on. So not all specimens can be made thin enough for the TM. Additionally, there is considerable interest in observing surfaces in more detail. So early attempts at producing images from the surface of a specimen involve mounting the specimen nearly parallel to the electron beam, which then strikes the surface at a very small angle, and only a very narrow region of the specimen appears in focus in the image, and there is considerable distortion. So technique has not found wide application in the study of surfaces. Electrons are easily stopped or deflected by matter. That is why the microscope has to be evacuated, and why specimens for the transmission microscope has to be prepared in a proper way. Or to understand the specimen, the thickness should be a few hundred micrometers only, sorry, nanometers only. So in that sense, what we are saying, that if we are observing the TM, the specimen, what do you do, or in what way you are doing, basically, a very simple example we are saying. Imagine yourself alone in an unknown dark room with only a fine beam torch. You have a torch, you have a big dark room. So what do? You might start exploring the room by scanning the torch beam systematically from side to side, gradually moving down so that you could build up a picture of the objects in the room in your memory. In the same way, a scanning microscope uses an electron beam instead of a torch, an electron detector instead of eyes, and a fluorescent screen and camera as a memory. So with that principle, basically, this the electron beam analysis of let's say TM happens. So very small beam spot, line to line scanning you are doing, and then only with the line to line scanning you are getting the proper image of few micrometers square only. Okay, and as I told you, some specifications we need. We need vacuum for the microscope, and what up to what order of microscope generally you need 2.5 × -5 Pascal. Okay, so just you can skip this idea. Then the electronics, means lot of electronics you need, because with all this process, how you are detecting, let's say, the electron hitting to the fluorescent screen, what this emission you are getting. Okay, so in that sense, the detector play a major role. For the detector, you need you have to face a lot of let's say signal to noise ratio problem, because if there is noise, you cannot get better information. So definitely, a better electronics is required for all these systems. So digital electronics technique is in general, and microprocessor based techniques in particular play an important role in this respect. So modern electron microscope employs a fast, powerful PC to control, monitor, and record the operating conditions of the microscope. Everything is controlled. Okay, so the results in a dramatic reduction in the number of control knobs compared with earlier models. So now with the software, you can control everything and you are getting the image very easily. Okay. Right. Most important thing, generally, what we have this specimen preparation, sample preparation, how you do the sample preparation. So what different type of samples, different type of objective have different idea. Okay. So that's why I would like to say that TM can be used in many branches of science and technology where it is desired to study the internal structure of a specimen down to the atomic level. It must be possible to make the specimen stable and small, nearly 3 mm, because there is a chamber where the sample could be kept. So generally, a small sample is required. Okay, and then you have in case of biology or in case of functional material science, you have different idea. Okay, so I can skip this part. Then this scanning TM, as I told, this technique can be applied in a SEM, but there is much more interest in applying it in TM. You have the TM and then you apply scanning electron microscopy. It is a better combination as compared to SEM converted to STEM. Okay, so this technique was first demonstrated by FEI company in 1969, and today most TMs can be equipped with this facility. So TM can give you transmitted image as well as scanning electron microscopy also. So both the things are combined. Okay, so the latest TM offers a resolution of the order of 1 nanometer of the magnification of more than 1 million times. Another important things with the latest microscopy or improvement in the microscopy, especially in the TM, when you have a very small sample, orientation and manipulation means along what angle, what direction you can have the possible structure. So in that system, generally you have a goniometer. Okay, so with that goniometer, you can change, you can you can you can change the position, like The goniometer is a specimen stage designed to provide, in addition to X and Y direction, translation of the specimen, tilt about 1 or 2 axes in rotation, as well as Z movement parallel to the beam axis. Any possibility is there. So that's why you can understand better, like Said pattern generally people are getting to understand the crystalline structure of the material. So you need these type of setup, goniometer setup with the system. So it is usual to provide for heating, cooling, and straining of the specimen for a specialized experiment in the microscope. So in case of these systems, now you have the heating arrangement, you have the cooling arrangement in advanced system. And okay, so the structural change, what is changing with respect to the temperature, with respect to this heating of the material, means you can see what changes is happening. So that's why little bit advanced microscope with these systems are also available, but we don't have here at NIT. Okay. Now this scanning electron microscopy, it also consists of electron optical column, vacuum system, electronics. Okay, so this is, I think I can skip. I already explained some more details. More interesting thing is how we are getting with the electron microscopy, means what is happening when you are hitting the electron. So what happens in the specimen during the electron bombardment? Okay, means you are just using the electron beam as a light. In case of light, you don't have that damage to the samples, but in case of electron beam, if you are hitting, there is a lot of other problems, other possibilities. So you have to understand what is happening with the electron bombardment. Okay, so specimen itself emits secondary electrons, number one. Some of the primary electrons are reflected, means backscattered electrons. Electrons are absorbed by the specimen. Specimen can emit X-rays. I will explain how it happens. Then specimen sometimes emits photons. That's why you have energy dispersive X-ray analysis, means elemental analysis with this SAM or TEM system. Okay, so all these phenomena are interrelated, and all of them depend on, to some extent, on the topography. Okay, the atomic number, the the chemical state of the specimen, the number of backscattered electrons, secondary electrons, and absorbed electrons at each point of the specimen depends on the specimen's topography, what type of sample you have. Okay, to a much greater extent that the other properties mentioned here, it is for this reason that these phenomena are exploited primarily to image the specimen's surface. Okay, so most of the time we are using the morphology of the surface, not in deeper material. So these electrons bombarded the specimen, cause it to emit X-rays also, and with that X-rays we are also having the detector, energy dispersive X-ray detector, and which could give you the elemental analysis of the materials. Okay, so it is just contrary to the case of light microscope. Maybe we are having different approach. So I think this is some I can skip. What is happening, that means what comes to the specimen is high energy compositional contrast with the backscattered electrons. So generally backscattered electron scanning give you high energy compositional contrast, and brightness of the regions in the image increases as the atomic number increases. Okay, now the less penetration gives more backscattered electrons. If penetration is less, it means backscattered electrons will be more. Okay, now if you say secondary electrons, these are low energy topographic contrast, and fluorescent X-rays give you the elemental analysis. Okay, so just schematic diagram here again I put that whenever the incident light is falling to the sample, whatever the specimen with the sample you have a different type of signals, means backscattered electrons, Auger electrons, or secondary electrons. So what you want is the detector which can detect only the secondary electrons. Generally in the SAM we have the secondary electron scanning, so the detector is detecting only secondary electron, not the backscattered electron. Okay, so range you have to fix, so the detector has to be very specified. Okay, Sometimes people are also using the OJ electrons, which is very sensitive, which surface sensitive in case of compositional. So if you know better composition, OJ electron generally the detection is better. But most of the time we are using secondary electrons. Okay, so, and for this X-ray generally the elemental analysis we do. Okay, and sometimes people are also trying to backscatter electrons. So sometimes the image could be better for the backscatter electrons. But these are the system which are having multi detectors. But generally, the system what we have in our lab, let's say it is only one detector system which is detecting only secondary electrons, and another detector which is detecting X-rays, means the photons, which is used for energy dispersive X-ray analysis in our lab at NIT Kurushetra. But some advanced system is having different type of this multi-detector system, and that multi-detector system give you better image sometimes. So that possibility could be there. So generally with the samples, how it's detect penetrating, up to what range it is penetrating, and how it could enter. So you can think of in case of let's say scanning electron microscopy, how backscattered, how secondary electrons possible. Okay, so backscattered up to what range it is possible, secondary electrons from where it is possible. Like OJ electrons, it is only on the surface only. Okay, and then if it is deeper side, we have the characteristics. So backscattered electrons is just an explanation. Maybe you know better. I can skip that. X-ray emission is based on the simple phenomena. If you hit the electron, move, and the higher orbit electron shift to the lower orbit, then definitely it emit the X-rays. Okay, so just an idea of the backscattered and all these scattering and what factors affecting the size of interaction. It means the diameter of the primary beam, energy of the primary beam, atomic weight of the specimen, means the target, what type of the target, and coating of the specimen. When you do the coating should not be very thick so that it should stop only on the coating. So you have to be very careful about all these systems. So just again the scheme of a TM here. So just I put all these scanning, is the electron microscopy, either SAM, TAM, or HR-TAM. It's almost the similar type of principle. You have the gun, you have the objective lenses, mean electromagnetic lenses. Okay, you have the projective lenses, and you have the this projective lenses means how you control the spot on the sample, and generally with the vacuum system, how strong the vacuum system, so that the less interaction with the electrons would be there. Okay, and this with the projection lens, you can have the same pattern, basically selected area electron diffraction pattern, and then on the basis of that you are getting the crystallite size. Okay, so it means this transmission electron microscope can be compared with the slide projector. As earlier I told you, I think it's just the same. And the same is the SAM or TAM, how you do the diffraction pattern, and how you do in case of SAM interaction. Is this just combined idea of the emission is transmitted electrons you are getting unscattered, elastically scattered electrons, okay, OJ electrons, all. So these signals are used for scanning electron microscopy, and these scattered electrons are used for the TM. Okay, so both that way it's possible. Now the magnification in case of electron microscopy, how you do it. So generally this sweep distance on the monitor and this E-beam scan distance on the specimen will play a major role on the case of magnification. That's why the spot and the distance between source to the specimen is important part. So it's sometimes vary with the scanning electron microscopy. Another important parameter what we should do when we do the scanning. Let's say here this cone angle, it should be small as possible. So if cone angle is small, you can have better, let's say, understanding. Or just an example of resolution is if it's port size like probe, that if it is small, it is good. But let's say if you have these type of sample, and the spot size is very big, you cannot resolve. So definitely a smaller probe size is required, it can resolve. So this probe has to be better as possible to get the better resolution. So resolution determined by the probe size or the diameter of the probe at the sample. So when it is this spot size, it is important. So the voltage at which are being accelerated as they travel through the electron, convergence angle, beam current, and diameter of the final beam spot on the sample or spot size play a major role in case of electron or transmission electron microscopy. Depth of field means definitely the energy will play a major role, and on the basis of that we can have the convergence angle, and on the basis of that convergence angle we can have the spot size, and then we can play with the magnification and all these things on the basis of that. Now, I told you the electron detection, more important. So the detector, what type of detector generally we are using for the same or time. So detectors for backscatter electrons and secondary electrons are usually either a scintillating detector or a solid state detector. In the case these electrons strike a fluorescent screen which thereupon emits light, which is amplified and converted into an electrical signal by a photomultiplier tube. And then this detector works by amplifying the minute signal produced by an incoming electron in a semiconductor device. And this specimen is not directly connected to the earth but a resistor, and the electrons that are not reflected generate a potential difference across the resistor. This changing potential difference can be amplified and the resulting signal used to produce a third sort of image on the monitor. This facility also permits the study of electrical phenomena in electronic devices such as integrated circuits. So different type of idea of detector system is possible. And the X-ray detection, X-ray analysis, so depends on type of detector you are using. Okay, so I can skip a little bit. Then other concept of the sources, what type of source, field effect, scanning or other source, what type of improvement you can do. These are just the idea, maybe you can skip that. Then observing of the recording of images, so image treatment, and up to what limit the vacuum is required for a particular image analysis. So sometimes some brief about this we can say the image treatment, because the image in a SEM is completely electronically produced. It can be subject to all kinds of treatment using modern electronics. This includes contrast enhancement, mixing of images from various detectors. Means sometimes you have 2 to 3 detectors and then you are getting the image. Okay, so these are some advanced microscope only, and subtraction of images from one detector to another type of detector. Coloring of the images is possible. The coloring is just because in principle you should have the black and white image, but you can play with that image and you can improve it with the software. Here the vacuum means in general a sufficient low vacuum of SEM is produced by either on diffusion pump or thermomolecular pump, in each case baked by a rotary pre-vacuum pump. So these combinations are also reasonable exchange times for specimen, filament, and aperture. So some this is a technical aspects. I think I can skip a little bit. Electronics, what we have, specimen orientation and manipulation. As I told you, with the goniometer we can play with that. What type of image you can have, movement of XY direction. Okay. Another important concept here also, environmental scanning electron microscope. In that case, the samples for conventional SEM generally have to be clean, dry, vacuum compatible, and electrically conductive. In recent years, the environmental scanning electron microscope has been developed to provide a unique solution for problematic samples. Examples of specimens which pose problems are wool or cotton tissue, cosmetics, fats, animals. So different type of people are using this environmental scanning electron microscopy, or in that case they are using particular environmental chamber. So this is not useful for material science people. So you can scrap this. Different type of phenomena, I think I already explained. The recording of image, as I told you, fluorescent screen, we have major common concept through a large window into the projection chamber. And in order to examine the fine detail or the correct focusing of the image, a special fine grain focusing screen can be inserted into the beam and observed through a high quality binocular viewer. Okay, so some advanced possibility in that system is also possible. We can have this idea about the image formation in case of electron microscopy, how it forms. So secondary electrons generally, as I told you, most of the system are using, and then movement of the beam line by line, means the raster movement is a very common phenomena. Means line by line you are using. So generally we say this, the raster movement is accomplished by means of all small coils of wire carrying the controlling current. So by using the scan coils, you can control the scanning. You can do it. And sometimes people are also using the cathodic luminescence image. Okay, so that is also useful sometimes for the scanning electron microscopy. Now, what are the factors affecting the image quality? Means in what way? Condenser lens and resolution. To increase the condenser lens current produces a smaller spot size and results in a better resolution. Increase the condenser lens current reduces the beam current, which results in less electrons for image formation. So there is more noise. Okay, so we have to think of up to what current possible. Stigmation, sorry. The stigmation causes the spot to be elliptical and produces distorted images. So that has to be taken care. Then working distance, as I told you earlier, working distance and resolution is directly related. So the working distance is the distance between the final condenser lens and the specimen. So decrease in working distance increases the resolution. Then working distance and depth of field view, in that case also you can change. There is some compromise between the two parameters. Accelerating voltage and resolution, again, if you increase the voltage, definitely resolution will improve, but you have to compromise somewhere with the other electronics. Okay, because there is again the charge accumulation. So if it's non-conductive, so negative charge forms the electron beam, tends to accumulate and thus affecting the final image. Some of the effects are abnormal contrast, appearing abnormal lines. So that's why these have to be changed. Okay. As I told you, diffraction pattern, side pattern is very important for the crystalline nature of the material. So in that case, just when a wave passes through a periodic structure whose periodicity of the same order of magnitude as the wavelength, then wave emerging is subject to interference, which produces a pattern beyond the object. This phenomena can be observed when a street lamp is seen through an umbrella. So it's a common, just to understand with the basic idea is how you are getting this side pattern, basically the selected area diffraction. Call it very common for crystalline structure. Okay, so in TAM generally people are using this skip. So some the difference between TM and SEM, the beam is not static as in the case of TM. With the aid of an electromagnetic field produced by scanning coils, the beam is scanned line by line over an extremely small area of specimen's surface. Then accelerating voltages are much lower in case of SEM as compared to the TEM. Okay, then specimens need no complex preparation. SEM is easily you can see, but for the TEM you need very thin sample preparation and more, let's say, taking care for the TM. So that's why SEM is more common to get the materials analysis. So SEM magnification, as I told you earlier, the length of the line by the electron beam on the monitor to the length of one track of the electron beam on the specimen. Okay, so just an idea about this. And there are applications. So I hope you all are material scientists. You understand there are a lot of applications. How to prepare the sample, what type of samples you are using. Okay, so for the SEM, let's say the size, and this is little bit depends on the type of the chamber you have. Okay, and then what type of, let's say, if you want to have a higher temperature, in what way you can give the maintain the temperature and all other things. So there are so many other possibilities uh, to think of all these concept of electron microscopy. Okay, so sample preparation. Just an example, maybe the resolution. Okay, so SAM 3 nanometer means getting, but up to 0.2 nanometer very easily you can get. And there are some sort of problems with this, means how we can get some defects. These are, let's say, give information of the internal structure. 10, SEM, not an optical instrument, but generates the images by analyzing the electron emitted from the specimen, gives surface information better. Okay, so this is how. And for the 10, the application is more to understand the crystalline structure, and if it is the lower side, we can get the applications. This is some picture what my student was doing PhD. It's basically from NPL. So this is the facilities available, National Physical Laboratory, Delhi. So they may be available. If you see here, the gap between the lattice to lattice. Okay, so the very accurate, means the size 2 nanometer. If you see, so this is 0.144 nanometer accuracy with the resolution you can do 0.12 nanometer resolution you can do. Okay, so this how the advanced facilities of this transmission electron microscope, we call it high resolution TM facility. Okay, so it means the resolution line by line 0.144 nanometer is possible. Okay, STEM resolution 0.17 nanometer. Okay, EDS 136 EV you can do. So very accurately you can measure. And it is all based on the basic phenomena of the resolution, the spot size, X-ray, characteristics X-ray. I think I already explained you earlier. What are the characteristics, common X-rays, in what way we play with that. So this is again the simple physics phenomena. We can, I think I can script that. And then the detection of X-rays when electrons have different energy and how you detect with the EDS. So elemental analysis through EDS is more important, and on the basis of that, you can have the elemental analysis. Maybe I can skip that. Combining with this EDS with the SEM allows the identification at microstructure level of compositional gradients at grain boundary, second phases, impurities, and small amounts of materials. Okay, so the concept is basically the beam spot where it fall, only that region it will analyze. You cannot give the EDS for complete the samples. If the sample is properly mixed, you get the information of a very small region, and on the basis of that only you give the information about the sample. So the analysis is for a very small sample analysis of this EDS. So that's why sometimes people are doing mapping. Okay, so EDS with the SAM system generally have limitations, or let's say the sensitivity up to what percentage of an element it can go. So the limit generally 0.1 to 8%. Also poor sensitivity for light elements, because if you go to the lower side, definitely emission is very poor, and that's why you have a problem. The resolution of X-ray energy levels limits the positive identification of certain elements like molybdenum and sulfur due to overlapping energy slots. Means molybdenum and sulfur both are emitting the similar type of energy. So that's why overlapping will take place, and you cannot identify between sulfur and molybdenum. Okay, so quantitative analysis is usually limited to flat, polished specimens. Unusual geometries such as fracture, surface, individual particles, and films on substrates can be analyzed, but with considerable higher, let's say, greater uncertainty. So error would be higher in that case. So this is just okay. So this is just elemental, some example of elemental analysis, EDS. So how you can get the elements and microstructural analysis with some different type of possible applications. This you can do few, let's say, images from by my students. Some micrograph is you can have, then dissolving limit, but possible you can do. There's a tetrapod prepared by my students, very popular image have. So you can see this all you can do. Okay, so this resolution and image quality you can think of very well with this SEM. You can have this all the SEM image basically, not the 10. But here this EDS spectra all. Another, I would like that elemental analysis also you can do. So one element is properly mixed, you have the image coloring, different type of color you can put, and you can get the information. Okay, so different type of shape, structure, more morphology very easily you can see, different type of particle size distribution with let's say histogram draw you can find. Okay, so this is all let's say the images simple we have. So finally we can summarize. The optical microscope is good enough for microstructures, but SEM is an excellent tool for high resolution surface imaging. GM has high magnification and more depth of field. Different elements and surface topography emit different amounts of electrons. Due to this, the contrast in the electron micrograph is representative of the surface topography and composition, and EDS makes the identification of quantification of the sample, and different type of models available that we have. Another advanced technology, just one image I saw, this is also available at NPL, helium ion microscope, because you are increasing the mass. So you are using, in place of electron beam, you are using helium ion beam, and that helium ion beam is more accurately you can handle, and because of the charge and all these things. So this is very, very advanced technology right now we have. So that's all. I think, okay, Dr. Sinha.
Yes, sir.
We can stop this up to the electron microscopy.
Yes, sir. You have given enough.
Okay. So that may be good, because otherwise, is one maybe stuff. Scanning probe microscopy is remaining maybe near future.
Thank you, Professor. Thank you so much.
Okay then.
Thank you very much, sir, for taking your time, taking out your time from your busy schedule to deliver a talk in AFMIT. And I hope, as mostly participants are young researchers, so they will definitely take benefit from the detailed introduction of all the microscopic techniques for their research work. And for participants, beside the sir's research, sir has published so many papers. Sir is very cheerful, energetic, and always ready to help. So if you can, I guess, if you want to ask some questions even after the session, I guess sir will help you. So फिलहाल के लिए, if anybody has some questions, queries, please ask. Dear participants, if you want to ask something, please ask.
You write your question in chat box.
So I guess सर फिलहाल के लिए तो I guess कोई क्वेश्चन नहीं है अभी.
So everybody must have exhausted. So anyway, thank you, Professor Ashavani.
Okay.
Thank you very much for starting our session, and I think things will go smoothly.
Okay, sir.
Okay, can you conclude?
Okay. Thank you. Thank you very much.
Thank you very much. Thank you all.
Announcement for second session.
So, dear participants, our next session will start at 3:30, and please join us before 15 minutes, so that we can, so that our session should go smoothly. And the instructions are same, that please don't share your screen in between the sessions. And so that, so then we will meet around, I guess, 3:15.
Okay. Okay, thank you, participants.
Thanks.